Hi, I'm Kade Bowers.
And I'm Matilde Garcia.
And this is Lab 10 lasers.
Woo!
The helium neon discharge tube to make a laser. So we have this exposed helium neon discharge tube with a flat mirror on this end and then an external concave mirror with a radius of 60 centimeters on this end. And to align it, to get it to laser, we sent another laser through the system, aligned the laser light this way with the light coming out of the helium neon tube until we saw it lasing. And the helium neon discharge tube glass is slanted right here at Brewster's angle, so the S-polarized light is reflected away, and so the P-polarized light becomes dominant in the laser cavity and what's emitted. We can calculate a Brewster's angle of about 56.3 degrees from the index of 1.5 of the glass. Then to find higher order modes, we added a crosshairs to the system, and then we added a lens to expand the beam that we saw, and we were able to find the highest order mode of 0.6. So we see 7 lines down and 1 this way.
For the lab, we look at an electric spectrum analyzer and a Fourier scanning interferometer to measure the beat frequency and longitudinal mode of laser. For our setup, we have our laser and it reflects off the first mirror and hits the Fourier Pro, and we can read what's happening there with the oscilloscope. Then we add the detector and we can get the beat frequency using the electric spectrum.
Using the oscilloscope, we found the free spectral range to be 0.45 milliseconds, and that was equal to 582.9 megahertz. And then we measured the beat frequency to be 7.72 milliseconds, and that was equal to 10 gigahertz. Using our beat frequency to be 582.9 megahertz, we used this equation to find the length of our cavity, which came up to be 24.4 centimeters. Then using our electric spectrum analyzer, we found the beat frequency to be 552 megahertz.
So if Fabry-Perot interferometer works, you have 2 mirrors set up, and some light comes in, and at some spacing, the light will constructively interfere and come back out, and that'll correspond to the peaks that we see. When we analyzed the laser light coming out of the laser, we found that it was linearly polarized.
For this part of the lab, we use a beam profiler to measure the beam waist, the location of the beam waist, and the divergence angle of the helium neon laser.
Z, we recorded different beam diameters in the x and y direction, then we square both of those to get a polynomial function. From that, we traced where the beam diameter hit 0, and using the last 3 points made a linear line. We found a beam waist location in y of 32.6 centimeters, a beam waist location x of 50.7 centimeters, a half divergence angle theta in x of 0.538 milliradians, a half divergence angle in y of 0.514 milliradians, and then the beam waist in the x direction was 374 microns, and the beam waist in the y direction was 392 microns in radius.